Hi everyone, welcome to Airmath, the channel where I explain aviation stuff with math and physics. And so in this video, I'm going to explain why pilots fly the aircrafts with indicated airspeed and why they don't use the true airspeed. And so exactly what I would like to explain is why today pilots keep using the indicated airspeed, which we know this is not the real speed of the plane, and why they can't use the true airspeed, which is the real speed of the plane, and when after all, today we have sophisticated instruments and systems that can display the true airspeed in real time. Example, imagine a pilot needs to climb at 260 knots. Why will this pilot maintain the climb at 260 knots indicated airspeed, and why not 260 knots true airspeed? And that's exactly what I'm going to explain in this video. So before we start, there are two things that I need to clarify. The first thing is we are going to review a lot of basic things. So bases that you think we can skip them and they are useless and that we know already. But it's very important that we cover them in this video because I'm going to make an approach which is a bit different from what we used to see in the teaching manuals and all this atypical theoretical books. And also I need to precise that when we are going to explain to answer to this question why pilots they fly the plane with the indicated airspeed and not TAS, we are going to connect as well the relationship between all the speeds, so from indicated airspeed, calibrated airspeed, equivalent airspeed, and finally the true airspeed, and to see what's the real relationship between all those speeds, again explained with math and physics. Okay, so let's start with this. So if you take an object in movement, that object, it will have a kinetic energy. That kinetic energy, it will depend on its velocity and on its mass. So the kinetic energy is equal to half multiplied by the mass multiplied by the speed square. So far, I'm not saying anything magical, okay, those are stuff that most probably we know. Now, if I ask you, what's the kinetic energy of fluid? Okay, the fluid, it can be gas or liquid. So the fluid, it's a quantity of mass in a volume. And you'll tell me, well, the kinetic energy of a fluid, it should be the same. So it's going to be half multiplied by its mass in a volume multiplied by the speed square. So as you can see, the kinetic energy of a fluid is the same kinetic energy as anybody, but the only difference is that when we multiply by the mass, it's going to be mass over volume. And the mass over volume, this we know it, it's called density. All right, and so another thing as well to know is that this kinetic energy, it has another name. It's called dynamic pressure with the abbreviation Q. And so now I see where I'm going is why is it a pressure? I mean, why the kinetic energy of a fluid is a pressure. So first, let's start by reminding what's a pressure. A pressure, by definition, it's a force over an area, a force over distance square. Okay, an area, it's a distance multiplied by distance. And a force, it's a mass multiplied by an acceleration. An acceleration, it's a distance over time square. Okay, so now if I simplify this a little bit, distance square, I'm going to rewrite it as distance multiplied by distance. So here I can get rid of the distance on the top and one on the bottom. And so I am left only with one distance. And I rewrite this as mass over distance divided by time square. So that's the pressure. Pressure, it's a mass over distance divided by time square. But if we now look at this equation of the dynamic pressure, well, half we don't care because it's a constant, it's a number. Density, the density, it's a mass over volume, and volume, it's a distance cube. And speed, it's distance over time, but it's speed square, so it becomes distance square over time square. So we square everything, all right? And if we simplify this, if you rewrite this differently, so we obtain that distance cube can be rewritten as distance square multiplied by distance. And so here we get rid of the two distance square, and we are left with mass over distance over time square. And so as you can see, this is indeed a pressure. So that's why the kinetic energy of a fluid is known as pressure, and it's a dynamic pressure because it's progressive over time. So, I mean, it's in movement, okay? It's something that has an evolution over time. Anyway, now that we explain why that's known as a dynamic, why it's known as a pressure, so we can rewrite as kinetic energy of a fluid is equal to the dynamic pressure, abbreviation Q, which is equal to half multiplied by the density of the fluid multiplied by the speed squared. And the air, here we study the air because when we fly in the air being a fluid, so the kinetic energy or the dynamic pressure of the air depends on its density and on its speed. But here for the first time, I don't want to speak about the speed of the air, but I want to speak about the true speed of the air, the true airspeed. I know that this sounds a bit stupid and ridiculous, but since we are trying to find the relationship between the indicated airspeed, what is indicated in the cockpit on the instruments, and the real speed of the air, so the true airspeed, so that's why I want to rewrite this equation as the dynamic pressure of the air, the kinetic energy of the air, is equal to half multiplied by the density of the air, multiplied by not the speed of the air, but the true airspeed of the air. Okay, I want to introduce the term of true airspeed because we are trying to understand the relationship between indicated airspeed and true airspeed. So now that this has been defined, let's see how we measure the speed when we fly. I know that you probably covered this in instrumentation or in AGK, but it's very important to remind it, mostly in the way how I'm going to show this and explain it. So actually when we measure the speed of the plane, what we do, we measure the speed of the air around it, okay? Because when you drive a car, we measure the speed of the wheels. But here we are not, when we fly, we are not rolling over the clouds, okay? I think this, you already know it. When we move in the air, we have that relative airflow around the plane, and that relative airflow has the same speed as the plane. And so we're gonna measure the speed of the relative airflow. And when we know the speed of the relative airflow, then we know the speed of the plane. And this is how we measure the speed of the aircraft, okay? So, let's go then to the next slide. So here I designed, it's a diagram that represents the system of the airspeed indicator, but very simplified system, okay? So what I did here, I did a casing, okay, a case. Inside of the case you have a diaphragm. It's a diaphragm that does an accordion instrument, okay, that expands and compress, okay, it will expand and compress. Here you have the pitot tube, which is connected to the diaphragm, and here you have all the mechanism attached to the diaphragm, which is also attached to the gears, to the needle, on the airspeed indicator, with some graduation that I did here. And here you have the static port, which is connected to the case. And so what you need to understand is that actually when you measure the speed of the air around, we are flying into, the plane is flying into an air mass, and so that air mass will penetrate into the pitot tube, okay, the pitot tube that you have here on the side of the aircraft, okay? So the air mass will penetrate, and actually what's going to penetrate is going to be the total pressure of the air, okay? And so as you can see, well, the total pressure of the air will penetrate, it will make expand this diaphragm, okay? And so which is going to push against this gear and to show an indication. So I'm going to do it again, maybe that went a bit too fast. So as you can see, the total air pressure penetrated pushes against the diaphragm, and that shows an indication. But there is a little problem with this system, is that actually when we bring the total air pressure, actually we bring two components. The total air pressure is actually the static pressure of the air, okay, that I put here in red. So the air static pressure, and also the dynamic pressure of the air, which is its kinetic energy, half multiplied by the density multiplied by the delta square that we just defined before. So far when you look at this, it seems to be fine, okay? So it's like, that's cool. I have the dynamic pressure, which is composed with the speed of the air. So then I can simply convert this dynamic pressure, or simply I can convert this total pressure with this given dynamic pressure into an indication. But the only issue with this little problem is that the static pressure is also applied on the diaphragm, and so the problem is that I cannot control the static pressure. Indeed, when we fly, the static pressure will change, because if you climb, the static pressure will decrease, if you descend, it will increase, and simply if you move forward, we are moving to places with different air static pressure, and even when we don't move, the meteor is changing constantly, and so the static pressure is also changing constantly, and so it means that when the static pressure will change, this is going to affect the diaphragm, which is going to affect your indication, although you did not change your speed. So let's imagine, for example, I'm climbing to a higher altitude with the same speed, and I have a lower, for example, static pressure, and so if I have a lower static pressure, then it's going to exert less force here, and so it will show lower indication. And so as you can see, that's a problem, right? That's a problem. I did not change my speed, but I have a different indication, and that's an issue. Say, okay, I cannot fly with this. I cannot have a variation of my indication of speed when I did not change my speed. So the real issue here is the static pressure, that we need to get rid of it. So how we do to get rid of it? So we're gonna compensate with a static pressure with its own value from the static port, okay? So we're gonna let the static pressure also to penetrate from the static port which is located here on the side, you see it here. I don't know why I did a circle here, but it's actually here, okay? And here, as you can see, it's not affected by the movement of the air, of the air mass flying into. Of course, it will have a little bit of fluctuation. That is, it will affect it a little bit, but we assume that it will not affect it. And so the static pressure will penetrate there, and so it's going to push against the diaphragm, and this is going to compensate, it's going to cancel the action of the static pressure, which is brought via the pitot tube. And so at the end, we are left only with the effect of the dynamic pressure. Is this clear for this? Okay, so I hope this is clear. So at the end, we only keep the effect of the dynamic pressure, and this is how, in a simplified diagram, this system works. So let's review. We said that what we bring in our pitot tube, actually we bring the dynamic pressure, okay, which is the kinetic energy of the air. So half multiplied by density multiplied by the TAS square. So we said that's the kinetic energy of the air. I know that we bring the total pressure. I know. But since the static pressure is cancelled, then I would like simply to assume that we bring only dynamic pressure. So the dynamic pressure is the kinetic energy of the air, which is going to push against this diaphragm, and this diaphragm will convert this kinetic energy to a mechanical energy, and that mechanical energy will result in an indication. So what does it mean? It means that actually your indicated airspeed is simply the dynamic pressure of the air, but expressed with the wrong unit, okay? So actually your indicated airspeed, instead of showing you the value of the dynamic pressure in hectopascal or millibar, or simply to show you the value of the kinetic energy in joules, it's showing you knots or kilometers per hour. So it's showing you the value of the kinetic energy with the wrong unit. So imagine that you scale yourself, you want to check your weight, and instead of showing you 80 kilograms, it's gonna show you, I don't know, 100 watermelon, for example. Okay, so now that we understood that the indicated airspeed is nothing else than the dynamic pressure of the air, then we can say in a simplified way that the IAS is equal to half multiplied by the density multiplied by the TAS square. And now we can start to see little by little the relationship between the IAS and the TAS. And now to explain you actually how this indication works in flight for a given task, I would like to put you in a scenario and explain how this airspeed indicator is designed for what conditions. So the airspeed indicator is designed for the first purpose to show speed, okay? And so imagine that my speed is 10 meters per second. I want this airspeed indicator to show 10 meters per second. I mean, that's the purpose of having an airspeed indicator, is to show the speed of the plane. But this is designed in condition where we simulate the density for sea level in ISA, in International Standard Atmosphere. And so when this airspeed indicator is designed, it's designed in conditions to show you the speed of the air displayed exactly the same on the indicator, where the density is equal to 1.225 kilograms per cubic meter. So when it's designed into those conditions, so let's imagine I'm building this instrument. Imagine that I'm the manufacturer, I'm going to build this instrument, and I realize this test under condition where density is 1.225 kilograms cubic meter, and let's say I move at 10 meters per second, and now, for example, it shows me 7 meters per second. Well, that's not good, so I need to make some adjustments. So I make a small adjustments, that's 8, that's not enough, another adjustments, 9. Now I make another adjustments, finally 10. So now, when I move at 10 meters per second in 1.225 kilogram cubic meters density, this shows me 10 meters per second indication, so that's good. My instruments is ready to be, is ready for use, to be installed in a plane, and so the pilots can rely on it. But anyway, let's imagine that now I'm going to a place where the density is less than 1.225 kilograms cubic meter, simply by climbing to a higher altitude, or simply when the temperature rises. The temperature will change throughout the day, the pressure as well will change throughout the day as well, from place to place, and simply with altitude. So let's imagine that now I will simply climb to a higher altitude where the pressure is less, and so if the pressure is less, the density will decrease with the altitude. But let's imagine that I'm maintaining the same indicated airspeed, okay? So I'm climbing with the same indication while the density is decreasing, but my indicator shows the same indication, so 10 meters per second. But if my airspeed indicator shows, if my indicated airspeed is still 10 meters per second, it means that I have the same mechanical energy. And if I have the same mechanical energy, it means that I have the same kinetic energy. And if I have the same kinetic energy, it means that I have the same dynamic pressure. But if I have the same dynamic pressure with a lower density, it means that the TAS is higher than what is indicated. And so it means that the TAS is not 10 meters per second, where it's going to be another value, it's going to be maybe 11, 12, 13, 14, 15, I don't know. Well, we don't know, we know how to calculate it, but for the moment I don't know, but it's going to be a higher TAS than what is indicated. So just to come back to this, so when the for a constant indicated airspeed, when the density is less, well, TAS is higher. Clear? That's all. So, and vice versa, when the density increases, TAS will decrease. And so if you look at this on a graph, okay, so this graph is speed against pressure, altitude, or temperature. And so this higher pressure, altitude, or higher temperature results in a lower density. So we saw that for the conditions, it's not always at sea level, I say, but for the conditions of the density at sea level in ISA, we saw that IAS is equal to TAS. Okay, so your indicated airspeed displays the exact value of the true airspeed. But when the density decreases, when the IAS is constant, with a lower density, well, TAS can only be higher. And I would like to make a break on this graph. This is a graph that we see on many teaching manuals and many lessons. But when you look at this graph, it looks like that the TAS can only be higher or equal to the IAS. It looks like there is no case where the TAS is lower than IAS. Well, that's a bit wrong, because actually it is possible to have a TAS lower than IAS, and that's not hard to do it. The only thing that you need is simply to have an extremely high density, and then you're gonna have a lower TAS. Okay, so if you have a density higher than the 1.225 kilogram cubic meter, then your TAS will be lower than the IAS. Clear for this? So I want you to imagine, for example, let's say on a winter day, you are approaching to an airport near sea level and you have a very high QNH. So believe me, the density will be so high that your airspeed indicator, the value on your airspeed indicator is higher than the speed of the air around the aircraft. Okay? So, let's now see what are the consequences if you are flying with TAS. Imagine, for example, I want to simply keep always the same TAS. Well, I will take this graph again, but I will keep the same TAS. And as you can see, when I keep the same TAS and I go to a higher altitude, for example, or simply when the density decrease, for the same TAS, when the density decrease, the IAS will decrease. And that's not good, because you will see that for the next slide, that it is very important actually to care more about the IAS than the TAS, to care more about the kinetic energy of the air around the aircraft than the speed of the air itself, okay? And so let's see this one together. So we saw that the IAS is equal to the dynamic pressure, which is half multiplied by the density multiplied by the TAS squared. And now if I ask you, for example, to write the equation of an aerodynamic force. An aerodynamic force, by definition, it's a force which is generated by the movement of a fluid around the surface or by the movement of the surface in a fluid. And this aerodynamic force will depend on the density, so half multiplied by the density multiplied by the speed squared, the velocity of that fluid, or simply the surface in the fluid, multiplied by the surface and the coefficient of force. The coefficient of force, it's a number that defines the ability or the capability of that surface to generate force in a certain configuration. So it can be the angle of attack, the profile of the surface, etc. And here, because we are speaking about the aerodynamic force generated in the air or by the air around that surface, so I write V as TAS squared. So anyway, when we look at this, this equation looks a bit annoying because we can change the speed. We can control the speed, but we can't control the density. And the thing is that the density being always variable, we don't know how much is the density and we don't know by how much we're going to adjust our speed to generate the same aerodynamic force. Okay, if you simply look at the density and the speed. So if the density decreases, to have the same force, we need our speed to increase, for example. But we don't know by how much, because we don't know simply by how much the density has been changed. But when we look at it, for example, with this point of view, if you replace this part of the equation by IAS, we see that actually we are going to generate the same aerodynamic force as long as we fly with the same indicated airspeed, and that resolves a lot of problems. When I speak about aerodynamic force, I can speak about the output from the ailerons or simply the lift or the drag are aerodynamic force, okay? Or the lift generated from the wings, or the output generated by the rudder or the elevator or whatever. Speaking about lift, let's look at this equation, for example, okay? Weight equal lift. And so the weight is mass multiplied by the constant of gravity, and the lift, we saw it before, and probably you saw it before, is half multiplied by the density multiplied by V squared, but here I would like to write TAS squared, multiplied by the surface multiplied by the coefficient of lift. And if I ask you now what's your stall speed, you tell me, well, the stall speed is TAS squared at CLmax. And here I just would like to make a reminder, please remember that we don't stall because of a speed, but we stall because we exceed the critical angle of attack. Okay, simply the stall speed is a speed when we go below. A further increase of the angle of attack to compensate for that decrease in speed will make you exceed the critical angle of attack. Okay, and so lead you to stall. And so, as you can see, when you look at this, equation, the stall speed is not that obvious. And for you as a pilot who needs to know your stall speed, well, it becomes a nightmare because the density is constantly changing in flight, okay, and constantly changing throughout the day. So if I tell you, for example, okay, I stall for this density, I stall for this much, but I tell you, yeah, but if you go to a higher altitude, the density will decrease, and so the stall speed has to increase. And so as you can see, it means that you have different stall speeds for each altitude, and that's a nightmare. Also, the density will change with temperature. And so the temperature will change with altitude, the temperature will change with time, okay? So it means that, for example, if you fly at 3 o'clock in the afternoon, the temperature is warmer than 10 o'clock in the morning, and so the stall speed at 3 o'clock in the afternoon is higher than the stall speed at 10 o'clock in the morning. Or simply, you're gonna have a different stall speed when you fly in tropical areas than over polar areas, because simply in tropical areas, the temperature is higher and so the density is lower. And that's a nightmare, okay? You can't know an infinite number of stall speeds simply because the density is changing. However, if I replace this equation with this, with IAS stall, so as you can see, your life becomes easier. And I want to say, thanks God we fly like this, okay? Thanks God we fly with the indicated airspeed in this case. So we simply need to know only one value. And so as you can see, when you go to a higher altitude, when I say not, of course, there is the compressibility effect, okay? But if you remove compressibility effect, if you just focus on subsonic flight, less than 40% of the speed of sound, as you can see, your indicated stall speed is constant with altitude, okay? And so as you can see here, we don't care anymore about the density or the temperature or the altitude. We simply, as long as the indicated airspeed is not, we don't reach that indicated airspeed, we know that we're not going to stall. But I know that you're going to tell me, you tell me, yes, but if I increase my mass, also this IAS has to increase. Yes, true. But if you know the highest stall speed for the highest mass that you can have, then you can stay safe under all conditions at 1G flight, of course. And so this is why the manufacturer will publish various stall speeds at different masses, but the most important mass that at which you need to know your stall speed is the highest mass that you can ever have, and that highest mass is simply the maximum takeoff mass at the CG forward. And if you want, I can explain in a different video why the CG forward makes the stall speed to increase. And so that's all. So the manufacturer will publish, for example, the stall speed at the maximum takeoff mass. So that's the maximum mass that you can ever have. And then, so that's going to be the highest speed at which you're going to exceed the critical angle of attack for that mass. Okay, as well, let's look, for example, at the drag equation. You see, if you look at the drag with half multiplied by density multiplied by v square multiplied by surface and coefficient of drag, this again doesn't help much, okay? Because, okay, for a given speed, you generate a certain amount of drag, but if the density changes, the drag will change, okay? And that's not reliable. However, what is reliable if I write it like this, and so as you can see again, as you can see, the drag is equal to IAS multiplied by surface multiplied by coefficient of drag. And so what does it mean? It means that provided that you maintain the same IAS, you're going to generate the same amount of drag. And that's why the aircraft performance are measured in IAS. Because why? For example, if we tell you that with this IAS, you're going to generate this amount of drag, and so for this amount of drag, you need this amount of thrust. And so for this amount of thrust, you're going to burn this much fuel. Okay, and so that's why the range and the endurance are measured in the POH, in the Pilot Operation Handbook, or in the AFM Aircraft Flight Manual. They are mentioned in IAS. That's why they tell you if you want to perform those performance, if you want to achieve those performance, fly this indicated airspeed. Simply maintain this kinetic energy of the air. That's the meaning of it. Okay, that's why, for example, VMDs and IAS. We tell you if you maintain this kinetic energy of air, your aircraft will generate the least amount of drag, okay? Not in TAS. TAS doesn't make any sense because when you change density, drag will change, okay? And that's why, for example, as well, this is something to know, the indicated airspeed it has another name. I don't know if this name is not very common, but it has another name. It's also known as performance speed. Okay, that's why, for example, the never exceed speed for the small plane, because the big planes, the never exceed speed, I mean, it's calculated with equivalent airspeed, but equivalent airspeed I'll explain a bit later here. But that's why for the small planes, the never exceed speed is in indicated airspeed and not in TAS. It's not TAS what is dangerous for the plane, but it's the amount of kinetic energy of air that the aircraft structure can absorb before or without having any structural failure. Do you understand? And so at a certain speed, the air will have a certain amount of kinetic energy that the aircraft structure cannot resist anymore, and so you'll have a structural failure. Okay, and so what we want is the kinetic energy of the air here, is the dynamic pressure of air. So IAS and not TAS. Because if you fly in space at 1,000 knots, I can promise to you that nothing will happen to the plane if you don't touch any debris, of course, from all those debris around. But if you fly in space at 1,000 knots, nothing's gonna happen. Because simply the kinetic energy of the air absorbed by the structure is very weak, the density is very little there. Okay? So that's all. So as you can see, this is the importance of flying with IAS. So as you can see, it is very important to fly with IAS and not with TAS. So what is TAS used for? TAS is used for only to obtain the ground speed after you calculating the wind, and then when we know the ground speed, then we know how much time it's going to take us to reach destination, and so how much fuel do we need to carry on board to achieve safely this flight. Okay, so that's only thing for what TAS is used for. That's it. But now let's look at this, so how we can calculate TAS when we know IAS, okay? So let's look at our equation again. Of course, this is very simplified. IAS is equal to half multiplied by the density multiplied by the TAS square. But if I ask you what's the TAS, you'll tell me, well, what is my indication? What is my indicated airspeed, sorry? My indicated airspeed, well, you look at your airspeed indicator here, for example, 110 knots. And imagine I have a machine that can measure the density of the air. So I measure the density of the air, and so you tell me, well, if you know your indicated airspeed, then you should be able to find the TAS if you know the density, right? Of course, that's not how we do it. I mean, that's not really how we do it. The real equation is this one, okay? I will explain this in another video, like to demonstrate why TAS is equal to IAS multiplied by square root of 1.031 power, the pressure altitude in 1,000, multiplied by 1.035 power, the ISA deviation. Okay, we'll explain this another time. But this is the real equation, relationship between TAS and IAS. And I want you as well to know something. Please be careful of that equation because it does not involve compressibility correction. And this is something we're going to speak about later as well. But anyway, let's come back now to my equation here. As you can see, here at this stage, I should be able to find the TAS if I know the IAS. But anyway, let's remind what is the IAS. The IAS is actually the kinetic energy of the air mass which is hitting the plane. But that air mass, as you can see, when it hits the plane, it will fluctuate around the aircraft. You saw this from POF. You saw that when the airflow crosses that venturi tube and when you change the cross-sectional area, its dynamic pressure will change. So here is the same, the dynamic pressure. It will, as you can see, the cross-sectional area, it will change because of the fuselage of the plane. And so the dynamic pressure of the air will change. And where you measure it, you see, that's the pitot tube. Where you measure it, you're gonna measure a changed value. You're not going to measure this value, but you're gonna measure a fluctuated value. Okay, you're gonna measure this value. And this value, as you can see, is not the real value that you are supposed to measure here. Is going to be a wrong value. And so if you put a wrong value in your equation, well, your result also will be wrong. And so here we say, okay, what is the problem of that? Why it is a wrong value? Well, it is a wrong value because of the position where you measure it. And where you measure it, you measure different pressure. And so this error is known as position or pressure error. Okay, so where you measure the kinetic energy of the air, where you measure the dynamic pressure, is not going to be the same that you're supposed to measure it in front of the plane. Okay, and so the indication that you read is not the real kinetic energy of the air because of the position or pressure error. As well, there is another error related to this, is when you look at the instrument itself, the airflow will fluctuate into that pitot tube. You see, it will encounter restriction, it will turn, it will fluctuate, and so that fluctuation, because of the instrument itself, will also be part of that error. Okay, so here, as you can see, that wrong indication here is wrong because of two issues: because of the position or pressure error, and because of the imperfection of the instrument itself. Okay, and so when we do those corrections, so when we correct for position instrument error, we obtain the real value that you are supposed to obtain, and this is called CAS, calibrated airspeed. And so the calibrated airspeed is actually nothing else than the real indicated airspeed that you are supposed to measure here. You understand? So your indicated airspeed is actually the fluctuated one, and the calibrated airspeed is actually this one. So when you put the calibrated airspeed in your equation, then you find the correct true airspeed. Okay? And so the calibrated airspeed, also it has another term, is also known as rectified airspeed, abbreviation RAS. Okay? Okay, so now that we understood what's the calibrated airspeed, let's imagine that now I have no mistake. Okay, so let's imagine that my my airspeed indicator shows this value. Okay, so there is no position instrument error, but IAS is equal to CAS. Now I'd like to speak about the compressibility effect. When an object is in movement, okay, for example, an aircraft is in movement, it will generate pressure waves, and those pressure waves will travel at the speed of sound. And I put here a wavelength lambda. So when the object is in movement, it will generate those pressure waves, and those pressure waves will be closer to each other ahead of that object in movement, so here ahead of the plane, and will be distant from each other behind the plane. Okay, so the wavelength here will be bigger than the wavelength in front. This effect is known as Doppler effect. And so what's happening actually, when you catch up with your pressure waves, when the pressure waves are close to each other here, you are compressing them, and so the pressure is rising. But when you don't travel fast enough, when you travel less than 40% of the speed of sound, we assume that there is no compressibility. We assume that those pressure waves are still distant from each other, and so the change of pressure is not significant. However, when you travel fast at 40% of the speed of sound or higher, you are catching up with your pressure waves, and so your pressure waves ahead are too close to each other. And so when they are too close to each other, you are compressing them, okay? And so when you compress something, what happens? You increase the static pressure. And so when you go sufficiently fast, you increase the static pressure ahead of you, and that's called compressibility effect. And so let's come back now to our airspeed indicator, to the system that I designed. So we saw that if I want to obtain my TAS from what it is indicated from my airspeed indicator, so here we assume that there is no instrument and position error. Okay, we assume that IAS is equal to CAS. Okay, so that's fine. But the thing is that when you travel fast enough, you're gonna compress here the pressure waves, and so you're going to increase the static pressure. And so what does it mean? It means that you're going to bring additional static pressure into the pitot tube, but that's not the normal static pressure of the air, okay? It's very important to understand that's an additional static pressure. And so you have an additional static pressure that you bring to the diaphragm, and so it's gonna push there in the diaphragm and show a higher indication. But the problem is that here, that additional static pressure, you can't compensate for it, because it's not the natural, if I can say it like this, it's not the natural pressure of the air around. It's an additional static pressure that you brought because of the compressibility effect. And so that additional static pressure will have its effect in in the diaphragm and will make the indication to increase. And so as you can see, this indication is now wrong if you want to obtain your TAS, okay? So if you rely to this indication to find your TAS, it's a wrong indication, and that's not good. And so what we do, we say, okay, we need to make a correction here, and that correction is called compressibility correction. It's just a mathematical correction that consists of removing mathematically this additional pressure. And so when you remove it, okay, I'll just do it again. So when you remove it, it's gonna tell you, okay, so actually your indication should be this one, and this is called equivalent airspeed. So what does it mean? It means that additional static pressure in the pitot tube will make the indication to be this one, but this indication is equivalent to this value. So to find your TAS, you need to enter the equivalent value to find the correct TAS. You understand? And so that's the equivalent airspeed. And that's why, for example, when you look at the maneuver envelope on the N diagram of the big planes, those diagrams are in equivalent airspeeds, is because once again what we want is not what is indicated but the kinetic energy of the air, so the dynamic pressure. And so here the correct value of the dynamic pressure for the planes that fly fast is not their indicated airspeed but their equivalent airspeed. So that's why when you look at the N diagram or the maneuver envelope of those big jets, they are measured in equivalent airspeed and not in indicated airspeed. Of course, and when I speak about this, I assume that there is no instrument and position error. All right? So I hope that now you understood. And so finally, let's imagine that now I want to find the true airspeed from the indicated airspeed. So we saw that the indicated airspeed is the kinetic energy of the air, but if you take the value that you read in the cockpit, we saw that value is wrong because of the instrument and position error. And so when we corrected, we obtained the calibrated airspeed. And so here is the real dynamic pressure of the air that you can input in our equation to find the TAS. But once again, when you fly fast, when the plane fly more than 40% of the speed of sound, we realize that again that indication is still wrong, that indication is still not correct, and so we need to correct for compressibility error. So we apply the compressibility correction to find that indication is equivalent to this value, and so that value is the real dynamic pressure of the air. Okay, see here I put Q, here I put Q, that the dynamic pressure of the air, and so that dynamic pressure of the air is equal to half multiplied by the density multiplied by the TAS square, and then we can calculate the TAS. But remember that to calculate the TAS, here is the equation. It's TAS, that TAS is equal to IAS, so TAS in knots, with the same unit. TAS in knots is equal to the IAS in knots, or both in kilometers per hour, if you want to keep this to kilometers per hour, multiply by the square root of 1.031 power, the pressure altitude per thousand, multiplied by 1.0035 power, the ISA deviation. But again, please put in mind that that equation, that formula does not include compressibility error. I hope that this was clear, and I hope that now you understood what's the real relationship between IAS, TAS, why we fly with IAS, and why we don't fly with TAS, and what is the link and the relationship between indicated airspeed, calibrated airspeed, or rectified airspeed, and equivalent airspeed, and finally the true airspeed. So that's it. This is the end of this video. I hope that you have enjoyed it. If you liked it, thumbs up. Don't hesitate to subscribe to my channel so you can't miss my videos. You can still leave me a comment, or you can put in comment which topic would you like to see me explaining with math and physics. And I'll see you next time for the next episode of Airmath.